Hello, everyone. I'm Marco Perone. I'm from Italy, and today I'm here to present the paper Crème de la Crème, Composable Representable Executable Machines, which I wrote together with my friend George Karachalias. The paper is mostly about the journey that I did in several years of working as software developer throughout software architecture and domain modeling. And it talks mostly about how I would like to be able to design applications. And it draws a lot of ideas from the domain-driven design community and the functional programming community. And it all starts from a workshop called Event Storming, which is basically a brainstorming activity which you do together to explore a domain of a greenfield or a brownfield application. You basically gather a lot of people in a room. I mean, a lot of people, all the stakeholders in the domain that you want to explore. You gather them in the same room. You provide them with unlimited modeling space, basically really big roll of paper or white wall, and a lot of sticky notes. And you basically ask them to describe using these sticky notes the domain following a timeline. And as you can see in this picture, the sticky notes have different colors, and every color has different meaning. So this is a kind of a legenda which describes the role of the different colors throughout event storming. And the most important color and the most important sticky notes are probably the domain events, which represent the facts, the things that happen throughout the application, and especially things which are relevant for the domain experts. And usually when you do event storming, you start from them, you start from events. For example, an event could be an add-on was added to a card, payment was completed, and so on and so forth. Then you start asking, what's the origin of these events, of these facts which already happen in your application? And the answer lies usually in commands, which are triggered by some kind of user of your application. And commands represent the user intentions, their actions, their decisions. And for example, they could be something like add this item to the cart, or process this payment, or ship this thing to this address, and so on and so forth. Another kind of sticky notes, which is the light brown down here, are called views, and they do represent the data needed by the user in order to make the decisions which they need to make to issue new commands. Then there are the yellow stickies, which represent aggregates, and the aggregates represent basically an aggregate of decisions. So aggregate represents decision which happens when a user triggers a command. So for example, a card could be responsible for deciding what happens, what really happens when a user requests to add a new item to the card itself. Or a payment aggregate could be responsible to decide what happens when a user requests to process a new payment. Then there are policies, which are represented by the purple stickies, which represent the reactive logic that could take place after an event happen inside an application. And the keyword which defines basically a policy is the whenever word. Basically, whenever you have the word whenever in a sentence, you can represent that with a policy. So for example, whenever an order is completed, we need to tell the shipping domain to process the shipping, or whenever payment is completed, we need to notify the user with an email or something like that. And the last piece are the green stickies called projections, which are the part of the domain which whose responsibility is to process events and to distill data which needs to be shown in the views. So basically, all the data of our application are stored in the events, and the projection just process them, filter the relevant data which needs to be shown to the user. And usually event storming is quite a chaotic process, but it usually creates a very nice representation of a domain. It's very nice experience to explore what a domain is. But another aspect of it that I really like is that it translates fairly easy into working software. So each one of these colored sticky notes, which I just described, could be turned into a specific component, into a software architecture in an application. And there are actually in the domain-driven design community a lot of practitioners which do use this kind of approach to build complex applications. But the main issues that I always had with such an approach is that with event storming, you get to realize, to achieve, to build some kind of artifact which describes, which documents your domain. But it usually is something which is fairly disconnected from the implementation itself. So even though in the beginning, the implementation will follow closely what you have in your event storming, what emerged from the event storming, as soon as the implementation proceeds and time passes and new features are requested, the two things begins to diverge. So the event storming representation will remain still, will probably not evolve, and the code instead will evolve and will change. New commands will be added, new events, new aggregates, maybe new processes, new views, new projections. And so you basically arrive at the point where your initial representation is something like a stale documentation, is no more faithful to what the software is doing. And so one thought which remained with me for a long time was how to solve this mismatch, how to fill this gap between these two aspects, the documentation you basically get from the storming and the implementation itself. And the first step to try to answer this question is to look exactly at this diagram and realize that even more than software architecture, this really tells about the role of the things which are involved here. So if you look at commands, which are the blue ones, events, which are the orange ones, and views, which are the light brown here, as data, and aggregates, policies, and projections as processes, you can see that this diagram here is describing the domain of an application just as the composition of some processes. And if you think a little more about that, you realize that these processes are almost pure. They mostly need to have a state. Actually, projection, they are usually pure. Aggregates needs to have some state involved, so they are just stateful purely stateful process. And policies, they usually have other side effects, but mainly they also are stateful processes. So stateful processes play a significant role in this architecture. The architecture is basically a composition of stateful processes. So talking of stateful processes, one common way of implementing stateful processes is using Mealy machines. A Mealy machine is a finite state machine whose output values are completely determined by the current state of the machine and the current input. And I always like the concept of a Mealy machine because it has, in my opinion, three really nice perks. So the first is that it has a really simple model, which is basically described by this record here. So it has a state, which here I call initial state, and an action, which is basically a function which, given an input, it can produce an output also depending on the state, and you also have the ability to update the state. So it's basically a stateful computation which consumes an input and produces an output. Then another perk is that a state machine allows, a Mealy machine in particular, allows a graphical representation. And this is extremely nice when you want to document and to represent things. So for example, a graphical representation that you could use for a Mealy machine is this one, where circles represent the possible states of your machine and the arrows represents the available transitions, where the numbers above the arrows, they do represent the inputs and the outputs of the machine. So for example, if we are in state S1 and we receive an input 0, then we move to state S2 and we emit an output of 1. We can even simplify this graphical representation, basically forgetting about inputs and outputs and preserving only the state transition. And we can get something like this. So this is basically the graph of the available transitions for a Mealy machine. And the third perk for Mealy machines is that they are extremely compositional, meaning that you can take two Mealy machines and compose them to obtain a third Mealy machine in several different ways. So for example, you can take two Mealy machines, one consuming inputs of type A and producing outputs of type B, and another one consuming inputs of type B and producing outputs of type C. And you can combine them to obtain a third Mealy machine, which just consumes inputs of type A's, uses the two Mealy machines in sequence, and then produces outputs of type C. Or if you have two Mealy machines, one from A to B and the other from C to D, you can compose them to basically run in parallel. So if you're able to provide to them an inputs for each one of them, so basically a pair of inputs, you can run both of the state machine, providing to each one of them their the input of the correct type. And then you can collect the outputs and basically output them in a pair. And so you can compose the two inner machines and obtain a bigger machine, which is basically the parallel composition of the two. And also, if you have the same two machines, one going from A to B and the other from C to D, you can compose them in another way. So for example, if you provide as input an either AC, so something which is either an A or a C, then depending on what you have as input, you can either trigger the above machine if you have an A, or if you have a C, you can use the machine below. And in the end, you will get as output either a B or a D, depending on the input that you had. And there are actually more ways you can compose Mealy machines, but this is just to give you an idea that they are extremely compositional, and they allow to build complex machines out of simple ones. So if now we agree, and at least I do agree with this, that Mealy machines are a nice way to implement stateful processes, the next question is, how do we encode a machine? So what's the concrete implementation for a Mealy machine? So if we look in the Haskell literature, basically we can find a package called machines where we find this data type. So the Mealy data type is a new type around a function which consumes A's and produces B's, and a new version for the machine itself. So basically, when you provide an input, you get out an output and a new version for the machine, which you can then use to consume future inputs. This data type is fairly nice and simple to use and understand, and it's also extremely compositional. For example, with it, you can have instances for the category type class, for the arrow type class, and for many type classes from the profunctor hierarchy. But this data type falls short when we want to obtain a graphical representation out of it. This is because what we have here is a function, and the only thing which we can do with a function is run it. We cannot extract any kind of insight about what the function itself, about the logic of the function itself. So we cannot generate some documentation, we cannot generate a graphical representation, we cannot somehow enforce that certain invariants are enforced in the execution of the function itself. And if we want to try to achieve these things, mostly the graphical representation is something that we would really like to get. What we could do is basically to add some more information to this data type. And the information that we would like to add is basically the collection of available transitions. So the transition which can fire during the whole life of the state machine, which is basically a directed graph, and we can just store all the nodes basically in this graph in a list, and have what I call the topology, which is, as I'm saying, the directed graph of the allowed transition of the machine. Once we have this information, we can decide where to store this information. So we could store this at the value level alongside as the running function for the state machine, but this is still some kind of an issue because there will still remain some kind of a gap between what's described in the topology. So in the topology, we will say we can perform these transitions, and the implementation itself of the running function of the state machines, where maybe we are actually performing a state transition which is not in this list. So this could be enforced manually, or maybe it could be enforced through runtime validation. So every time we want to fire a transition, we will need to check if that transition is actually present in the topology or not. And if not, we will need to do some kind of error handling procedure. We could also have another option, which is basically storing the topology at the type level. If we do so, and we create a data type like the one that I'm showing you right now, where we have the topology at the type level, we can use the topology for several different things. So we can use the topology to actually generate graphical representation for the implemented machine. And we can also use the same topology to make sure that the implementation of the machine is only firing allowed transition, and we can do that at compile time. So we're absolutely sure that when we run the machine, only transition present in the topology could be fired. Still, doing such a thing creates a little bit of an issue with respect to compositionality. And the issues are actually two. The first one is mostly technical, because now we have three type variables in our data type, which are the topology, the inputs, and the outputs. And having three type variables, we cannot have instances for all the type classes which relate with compositionality. So we cannot implement an instance for category, not for arrow, not for profunctor, and so on and so forth. And the second issue is that once we have the topology at the type level, and we try to compose two machines with that type, we are forced to compute the topology of the resulting machine at the type level. Well, that's not impossible to do. It's still hard. So it's not that we are completely losing compositionality. We can compose machines, but it becomes hard pretty quickly. So potential solution to this issue is to basically somehow forget in our main data type about the topology and introducing a new data type, which I call state machine here, where we have as type variables only the input and the output. So solving the issue that we had when we had three type variables there. And basically create a free structure over the previous data type, which I showed you. And so we will have basically the basic data type, which would enable us to create the leaves of an abstract syntax tree. And to create this basic state machine, we will need to provide a state machine, a Mealy machine of the previous data type. So a state machine which knows about its topology. And then we could use the other constructors to represent the composition operation that we might have. So for example, we could have a separate constructor for sequential composition, another one for parallel, one other for alternative, and so on and so forth. And doing so, what we get is basically an abstract syntax tree of compositions of Mealy machines, where the leaves are Mealy machines aware of their topologies, and the other nodes are just describing how to compose the subtrees. So for example, machine 1, machine 2, machine 3, and machine 4 in this diagram are all machines which are aware of their topology. And then the parallel, alternative, and sequential boxes that you see there just describe how we need to compose their subtrees. So for example, machine 1 and machine 2 needs to be run in parallel. Machine 3 and machine 4 needs to be composed sequentially. And then we need to execute in alternative the result of the first subtree and the second subtree. And once we have this abstract syntax tree to actually use it, we need to interpret it. And we could actually interpret this in several different ways. The two main ways are, well, actually for running a tree of machines and for creating a graphical representation. So when we want to run, basically we need to say how to run the leaves. And then given the knowledge of how to run the subtrees, how to run, for example, a parallel box, on how to run an alternative box. So knowing how to run machine 1 and how to run machine 2, we can say that, well, if we want to run them in parallel, just run them both and collect the outputs. Or if we want to run machine 3 and machine 4 in sequentially, as we are saying here, well, first run machine 3, then run machine 4, providing as input to machine 4 the output obtained from machine 3, and so on and so forth. Something similar could be done with a graphical representation. So we need to say how to create a graphical representation of the leaves, but since the leaves are aware of their topology, we can use their topology to create a graphical representation. And then we need to say how to create a graphical representation, for example, of the parallel composition of two machines, given that we know the graphical representation of the two machines. And we actually have different ways of doing this operation. We can basically create the state graph of the composite machine, or we can use this basically to represent basically really in parallel, showing two boxes, one on side of the other, showing that these two machines will need to be operated in parallel. And so at this point, with this data structure, what we achieve is we were able to use the simple model provided by Mealy machines, even if we add this topology concept to it. But I would argue that it does not complicate too much things. We were able to get a graphical representation of our machines, and we still have the ability to compose them as much as we want in several different ways. So basically, we were able to achieve all the perks that Mealy machines offer in one single data type. All these ideas, which I just talked about, are implemented in a library called Crème. And at this point, I would like to show you basically how you use Crème. So basically, I would like to show you Crème from the user's point of view. So suppose now, just for the sake of the example, that we want to implement a checkout procedure of some kind of an e-commerce. So basically, we receive a request to process payment, and we need to process it. And maybe at the end notify someone else that the payment has been completed correctly. And so we want to implement it using the architecture which I described in the beginning. And we will start trying. So we will need to implement 3 state machines: an aggregate, a policy, and a projections. So let's start from the aggregate, which is the one which basically decides what to do when a user emits a command. It decides what really needs to happen in the application, emitting some events which describe what really happened. And so for the sake of the example, we will have 2 commands. One will say pay the card, and the other will say mark the card as paid. And 2 events, one called initiated, will say, okay, the payment procedure just started, and the other completed would say, well, everything went smoothly and we're done with the payment. And to implement the state machines which describe the aggregate, as the first step, we need to define the topology. And to define the topology, we need to define the vertices of the directed graph of the available transition of our state machines. And actually, we'll have 3 vertices waiting, which is the initial state before everything starts, initiating, and complete. And then the topology itself is saying that if we are in a waiting state, we can only go to initiating. If we are in an initiating state, we can only go to complete. And if we are incomplete, we can go nowhere else. So we cannot go back to waiting and initiate. And at this point, we need to define an intermediate state type, which in this case is basically isomorphic to the vertex type, but in more complex cases allows basically to store more data inside a single vertex of the topology graph. And once you have defined this data type, you can really start to implement the state machine. And to define the state machine, you need to define the initial state, which will be waiting state. And then you need to perform the action. And to define the action, you need to say, okay, when we are in the waiting state and we receive the pay card command, we're gonna emit the initiated event and we are gonna go to the initiating state. Or for example, when we are initiating state and we receive the mark card as paid command, we will emit the completed event and we will go to the complete state. In every other case, we just do not modify the state and we do not emit any event. And then we need just to wrap our, we basically need to lift our topology aware machine, which is the leaf of our tree, to the state machine data type. After that, we have the policy, which is basically a payment gateway, which is that part of the application which reacts to the events to request new commands to be executed. And in this case, what happens here is extremely simple, maybe too simple. What we are saying here, every time we receive an initiated event, so saying that the payment procedure just started, we will ask the application to mark the card as paid. So basically saying that every payment will go through smoothly. Usually this is the place policies where you interact with external systems. So in reality, this would be something which would call an external, probably payment gateway, which will return you some result, which will you use to trigger the mark as paid command, or maybe do something else. And in the end, you have the projection, which is just going basically to project to the user the data contained in the events. In this case, what we want to tell the user is whether the payment is in the initial state or in the final state. And also this is basically a pure function saying that when we receive the initiated event, we go to the initial card view value. And when we receive the completed event, we go to the final state. And at this point, we implemented our aggregate, our policy, and our projection. And what we need to do is basically compose the 3 of them to get the representation of the whole domain of the application. And the application is nothing else than another state machine, which is obtained just by composing the 3 state machines that we already have. So first, we composed the card and the payment gateway, so the aggregate and the policy, in a feedback loop, basically saying every event will trigger the policy, which will create new commands, which will trigger the aggregate, which will create new events, which will trigger the policy, and so on and so forth, in basically in an infinite cycle. This will be basically the right model of our application, and then we can compose this together with our projection, which is payment status, here to create basically the whole application that we have. And as soon as we have that, we can use the functions provided to us by the Crème library to generate a graphical representation of our domain. And what you can see here is that our 3 boxes, one for the card aggregate, one for the payment gateway, and one for the payment status projection, each one of them containing the possible state transitions that can happen inside that state machine. So a card is the only one which has a non-trivial topology. The other 2 are just have one single state. And then you have the arrows connecting the boxes, representing how the state machine are connected. So if you remember, card and payment gateway were connected in a feedback loop. So you see the 2 arrows going back and forth between the 2 machines. And then card and payment status were basically connected some kind of sequentially. So first we do card and payment gateway, and then we perform with their output, we perform the payment status. Basically, that's all I got for you today. The paper is already online on the ACM digital library. And if you want to take a look at the code and more examples, you can just go to the repository of the Crème library. And if you have questions or any kind of feedback, I'm extremely glad to receive it. Anywhere you can find me on the web, you got here my email and my blog and my Twitter account, my Mastodon account. And I'll also be happy to answer some questions live now.